Oh, good morning. Let's see. Um, One student here. Let's see, I've got test graded and I'm going to be emailing those out to you this afternoon. Takes a little while to send 14 individual emails. Let's see. I think I only had 5 people turn in the multi-page PDF assignment, so I've extended the due date on that one until Monday because I very much want everyone to master it. So I'll be extending that so everybody can try that and please learn how to do it. It takes way longer to grade a test that's a poorly done PDF than it does one that's not, that's one that's easy to read. So anyway, today I wanted to do some problems. Two-body problems is what I'll call them, and they're the ones where you'll have like a mass sitting on a tabletop and another one that is hanging from the tabletop, and they're connected by a cord that goes over a pulley somehow. And I'd like to do a series of those, some without friction and some with friction, so we get the hang of dealing with those things. And I'll just dive in and start doing those. Let's see. I guess we can just go straight to that thing. And don't panic at this. That's stuff we were doing in engineering physics today. So okay, so for the first problem, I'll imagine that we have some sort of just a horizontal tabletop, and hope that's visible. And this will be a nice thick table, I guess. Anyway, and I'll put a little gadget up here with a pulley on it, and then there will be some mass on the tabletop, and the cord goes over the pulley. And what you sometimes see on the descriptions of these things is that it is a frictionless, massless pulley. So we can ignore the pulley. Its only purpose is to change the direction of the tension in the string from horizontal to vertical, or from vertical to horizontal. So it doesn't slow things down at all. So we can ignore that. And let's just suppose we'll start with both of the masses being 5.0 kilograms. And so, for our first example, we'll assume there is no friction between the mass that's on the tabletop and the tabletop. So we'll have that. Now, here's what I do when I have a problem like this. I make free body diagrams for each of the two masses and work until I've got things as simplified as I can get them. And then at some point, I'm going to have to combine the two things. So we'll just see what that looks like in this case. And I'm going to work on a separate sheet of paper here, just because, I don't know, I'm always running out when I try to cram it onto one table. So for the mass on the tabletop, if I look at the forces that are acting on it, well, it's on Earth, so one of the forces is going to be mg. And in this case, because the two masses are equal, I'm just going to use m to represent 5.0 kilograms. It's sitting on a tabletop, so another force that's acting is the normal force, and so I have that. Then another force that's acting in this case is the tension in the rope that's attached to that thing. And I'll call that T sub L because this mass is to the left of this mass. And that's the only reason that I'm picking the letter L on there. So that's what I have for that one. Now, something I often do when I have a problem like this is I write Newton's second law in vector form first. And vector form just means I take each one of the forces, and Newton's second law is that the sum of the forces is equal to ma. Now, this means the sum of. That's just a generic version of Newton's second law. It applies to every situation. For this particular situation, the forces are going to be N plus T sub L plus mg, which needs an arrow on it. So N plus T sub L plus mg is going to equal ma. And so that's Newton's second law in vector form. Then I take it and split it into components. I'll pick a direction for x and a direction for y, and I'll let x point to the right and y point upward. And then I write Newton's second law in each of those directions. And the first thing I would do is for the forces in the y direction, okay, which are the normal force and mg, the sum of those forces is going to equal 0 because nothing happens in the y direction for this mass. It's going to move sideways. It's not going to move up or down. It doesn't fall through the table and it doesn't jump off the table. And so that just tells me that if something points in the direction of the y-axis, it gets positive n, and if it points opposite the positive y direction, it gets a minus sign. This just tells me n minus mg is equal to 0. Now, for this problem, that's not going to help me at all. I don't need this bit of information, but for future problems, I'll do that, and it'll tell me what the normal force happens to be, because when we introduce friction, we're going to need that. So, but I'll stop here with the y forces. But in the x direction, the sum of the forces in the x direction, well, there's only one, but that's the one that causes the acceleration. And so it'll be ma. And then the only force in that direction is T sub L. So I can just say T sub L is equal to ma. That's as far as I can go with the mass that's sitting on the table. I don't know what the tension is in the cord. I don't know what the acceleration of the mass is. And so effectively I have one equation, but it has both of those unknowns. And when you have two unknowns, you have to have two separate equations to be able to figure them out. Oh, I should call this A sub L because it's the acceleration of the left mass. Okay, so that's what I can do with that left mass, the mass that's sitting on the tabletop. I can do something similar for this, except it's got a simpler free body diagram. Whoops, I always start with the weight, or almost always. Anyway, it's got the weight pulling down on it, and it has a tension pulling up on it as well. So I'll call that one T sub R because it's acting on the right mass, the rightmost mass. All right, well, when I have a two-body problem, I don't have to use the same coordinate system for each of them. And in fact, I think I'll go ahead and solve this the way I usually do. I know which direction this thing's going to accelerate if there's no friction up here. This mass is going to accelerate downward. This mass is going to accelerate to the right. For that hanging mass, I'm going to let down be positive. Okay, and so Positive is downward. Because the forces are both acting vertically, I can deal with this one one-dimensionally. And so if something points in the positive direction, it's positive. If it points opposite that, it's negative. But Newton's second law in this case is just the sum of the forces is going to equal ma, and this would be ma sub r is what it is, because it's the acceleration of the right mass. Well, the sum of those forces, when you write it as a scalar equation, you don't put plus signs between them. You indicate their directions with a sign. So any force that points downward is positive, any force that points upward is negative. And so I'll just get mg minus t sub r is going to equal ma sub r. And that's Newton's second law. It's in scalar form for this one. And this minus sign tells me that that tension in the rope on this one is fighting the weight of that hanging mass and won't let it accelerate as fast. All right, well, I have two unknowns here. I don't know T sub L or A sub L. I don't know T sub R or A sub R, but I can simplify things. These two masses are tied together by a cord. If this mass is accelerating downward, it'll have a positive acceleration. If this one is accelerating to the right, it'll have a positive acceleration. And because of the directions that I chose for positive for both of these, A sub R will equal A sub L. If I had chosen up to be the positive direction on this one, they would have had opposite signs. And that's something that I always work for when I'm solving these problems, is to make them both have the same sign on their accelerations. And I'm just going to forget about the A sub R's and A sub L's, just call that A. Another simplification is when I have a frictionless, massless pulley, turns out the tension is the same in both parts of the string. Now, it doesn't point in the same direction, but as scalar quantities, T sub R with no arrow and T sub L with no arrow, they happen to be equal. And so I can say that T sub R is equal to T sub L is just plain T. Whoops, why did I write A? It's just plain T. Okay, now here's what my equations become. I've got that T is equal to MA for that horizontal for this one, and MG minus T is equal to MA for the right one. Well, let's see. Can I do anything with that? Since this is equal to this, I can say that mg minus ma is equal to ma. And if I add ma to both sides, I've got room on this page. Just ignore this. That was yesterday's stuff. Or, nope. Yes, it was, I think. No, that was physics, engineering physics. All right, kick that MA across, and I'll get mg is equal to MA plus MA is 2MA. And, oh, the two masses are equal, so they just divide out. What I'll get is, dividing those out, divide both sides by 2, I'll get that A is equal to G divided by 2. Or if I'd left the masses in there, it would have been mg divided by 2m. Now, here's what's going on. Mg, that's the weight of this hanging mass. That's the force that's doing the accelerating there. 2m is the total mass that has to be accelerated. So the weight of this hanging mass has to accelerate not just this mass, but it also has to accelerate that. And so that's something that we have going here. But anyway, the acceleration ends up being 1/2 g. Now I'm going to go back to this expression right here. As far as the tension goes, the tension is equal to the mass times the acceleration, but the acceleration is 1/2 g. So I'd get m times 1/2 g, or 1/2 mg. And the tension is not equal to the weight of this mass. It's only half of it. When that mass is accelerating downward, the tension in the rope will be less than the weight of that thing. The tension is not enough to support the weight of this, and so it accelerates downward. So all kinds of things come out of a problem like this. Now, I didn't actually have to plug in any numbers because the mass ended up dividing out, but 1/2 g would be 9.81 meters per second squared divided by 2. So that would be the acceleration. So that was one with no friction. Now, let's introduce friction, and I'll have a complicated new diagram that I have to draw. We'll see what happens in that case. So now we ignore the bottom half of this sheet, and over here, have the same tabletop. Put a pulley on it once again. String coming over the pulley and going down here. 5.0 kilograms. Pulley comes up here. And I've got 5.0 kilograms. And I'm going to have a coefficient of kinetic friction here of 0.15. So just because. Okay, and then let's see what I have to do with the problem when that's the case. Okay, so it's still a two-body problem, but what's it going to look like when I do this? Well, again, for a while, I'm going to split this into two parts and study to the two masses individually. So now, for the one that's on the tabletop, I'll have its weight pulling downward. I'll have a normal force pushing upward on it. Okay, and that's just the atoms in the top of the tabletop repulsing the atoms in the bottom of the mass and holding it up. And we know these two are balanced because it doesn't fall through the table and it doesn't jump off the table upward anyway. Eventually it may go off the table when that one pulls it far enough, but we'll see. And then it's tied to a rope that probably has some tension in it. So I'll call this T sub L again. And then this one has friction. And so I'm going to just write that as a force to the left, and it's sliding. That's why I can use kinetic friction. And so that'll be a force that opposes the sliding to the right. And so anytime something is sliding, the frictional force, if there is one, is pointing opposite the direction it's sliding. So I've got these four forces acting here. With this one, Newton's second law in vector form now becomes the sum of the forces equals ma sub L, and I'm giving it the same subscript that I did last time. Well, those forces in vector form look like N plus T sub L plus F sub K plus mg, four forces. equals ma sub L, but I'm going to split this into two parts. And the first thing I'll do is look at the forces in the y direction where nothing happens. The sum of the forces in the y direction are equal to 0. I need to pick a direction to be positive for y, so I'll just draw a little x and y axis here. Okay. X will be positive to the right, y will be positive up. And in the y direction, n points up, it's positive. So n, mg points down, that makes it negative, n minus mg. And there is no acceleration for this this mass on the tabletop in the y direction. So those forces must cancel each other out. They equal 0. And that means the normal force is equal to mg. In this problem, I need to know that. Okay. All right. Well, what about the forces in the x direction with x being positive to the right? I'll have T sub L. This is a scalar equation now. The sum of the forces in the x direction are going to equal ma sub L. But what I have for forces, when I'm adding up the scalars, I indicate the directions with signs. So T sub L plus F sub K actually becomes T sub L minus F sub K in a scalar equation. Let's see, and that'll equal ma sub L. And that's just about as far as I can go, except I can simplify a little bit because that frictional force, it's sliding, is going to equal mu sub k times the normal force. And the normal force is mg. So that will equal mu sub k mg. Okay, well that will give me something to substitute in here, because this is a number I can calculate right now. It's not an unknown. So I can say T sub L minus mu sub k mg is equal to m a sub L. So that's as far as I can go on the left side. But that's quite a ways. I still have two unknowns in a single equation, though. I don't know a sub L and I don't know T sub L. So to get those, I have to consider the hanging mass here. And let's see where that will take me. A free body diagram for the hanging mass. Mg downward, and this time T sub R upward. By the way, why can I not say that T sub L is equal to T sub R when I put arrows on top of them? Wild guesses? Well, look at their directions. T sub L points to the right. T sub R points up. So they can't be true as a vector equation, but as a scalar equation, just like in the last problem, eventually I'm going to say these two are equal as scalars, just not as vectors. I expect this thing to accelerate downward, and I want to choose the downward direction to be positive so that if this accelerates to the right and this accelerates downward, then they'll both have the same sign for their acceleration. So I'm just going to let positive be downward again. And then the sum of the forces in the y direction here, this can be the y direction for this one, is going to equal m times a sub r. And what I have for forces is this one's positive, mg minus, this one's negative, so minus T sub r is equal to ma sub r. So what do we have in this case? I look at my two equations. And actually, here's the finished off equation on for the left mass. It's got T sub L and A sub L, things that I don't know. But again, a massless frictionless pulley, and as scalars, T sub R and T sub L are equal. Okay, when I don't take into account their direction, just their magnitudes, those two are equal. I'll call them T. And similarly, A sub L and A sub R are equal as scalars, things that don't have direction, and I'll just call them A. So these two equations are now going to look like, if I rewrite that one, mg minus T equals ma, and T minus mu sub k mg is equal to ma. Or if I kick this across, I can say that T is equal to ma plus mu sub k mg. Okay, that's what T is equal to. If I plug it in here, substitution, I'll have a single equation that says mg minus, now I have to be careful. I've got two terms here with a minus sign in front of them. I'm going to wrap those in parentheses so I make sure I distribute. Ma plus mu sub k mg equals, that was mg minus T equals ma. And now if I distribute that minus sign through, mg minus ma minus mu sub k mg is equal to ma. And one of the things, the only unknown left in this equation is a. And so I want to get the two terms with that on one side of the equation. And I'll get mg minus mu sub k mg is equal to, when I add ma to both sides, I'll get 2 ma on that side. And I usually do that kind of in my head. I don't bother to write like plus ma under this and plus ma under that. Although I'm just doing that in my head, but it works. Anyway, here's the thing. If I divide by 2m, and I'm not going to cancel out the m's at first, but I'll have mg minus mu sub k mg divided by 2m is equal to a. And this is a little more complicated than the last problem. In the last problem, somewhere, I just ended up with the acceleration was 1/2 g. I could divide out the m's here, but it's going to be a little more complicated here because I have this force, which is the weight of that hanging mass. That's the force that's making things accelerate, but it's working against the friction that's acting on that top one. And so that's what I end up with in this situation. This is like F net over M total. Okay, the numerator here is the net force. It's the hanging weight minus that frictional force that it has to overcome. The bottom is the total mass that's being accelerated. Both of these masses get accelerated in this case, so I have to consider both of those. And so, not quite so simple. All right, let's try one more problem like this. I'm gonna make things a little more challenging this time by introducing an angle. And I think this may be similar to one that was on the homework, but I'll just make up some numbers for this one. I'm also gonna give us different masses this time. And so let's suppose that we have something that looks like this, and I've got M sub L here. I've got a pulley, and so there's a cord that goes up to that pulley and then comes down here, and I have M sub R here, and let's let M sub R be 12.5 kilograms and M sub L be 6.0 kilograms. And I will put a coefficient of kinetic friction here, 0.10. Now I kind of expect that because this mass is twice what that one is, that it will accelerate downward. Oh, that's a 0.10 there anyway. And so I'm going to take that into account. Oh, something I don't know yet or haven't given you yet is the angle of incline that I have here. Let's put an angle theta on here and let theta equal 45 degrees. Okay, and so I'll have to take all of this stuff into account. This is a more complicated problem, but I'll start with making free body diagrams for these two again. Make a free body diagram for that one. It will have mg acting downward. Now, when I have forces that are acting at angles, I kind of try to indicate a couple of directions on here. This will be the angle theta, because the tension is actually acting up that angle. And so this would be the tension that's acting on the left mass, and it makes an angle theta with the horizontal. Now, the normal force to a surface, normal is a word in mathematics that means perpendicular to. The normal force that's acting on that, that's produced by the surface, is perpendicular to the surface. It's not going to be pointing opposite mg this time. And so that's going to throw a wrench in the works. And somehow we're going to have to take all of this into account. So there's my normal force. But I'm not done yet. There's friction acting on this thing too. And so now I'll have to have a frictional force. It's going to slide up the plane, I think. And so the frictional force will actually be down the plane. And so there's my F sub k this time, acting down the plane. Oh boy, this is complicated just by itself because I've got angles thrown in here and all this other stuff. But I'll show you something that I do on these to keep it from getting too bad. One is, I'm lazy. I pick a coordinate system for this one that's on the tilt that minimizes the number of forces that I have to figure out components for. And here's what I'm going to choose. I'm going to choose X to be up at an angle that way. And so it makes an angle theta with the horizontal. And I'll let Y be perpendicular to the plane. And when I do that, I don't have to figure out components for T sub L, N, or F sub K. The only one I'll have to figure out components for is mg, because it's cattywampus with respect to this thing. And I'll show you how I figure that out, but we can do it anyway. Now, I usually start off with Newton's second law in vector form just to kind of remind myself of what's going on. And that just means the sum of the forces as vectors equals ma. Well, the forces are mg, f sub k, n, and t sub l. So this part is just sort of repetitious each time, but okay, and that'll equal, oh, it's m sub l a this time, n sub l a sub l, actually. So that's different. All right, then what? Let's see. Now I start splitting these things into components, but I'm going to make a picture first that'll help me figure out the components of mg. And here's the deal. This angle is theta. This goes up the plane. This is perpendicular to the plane, but in that direction, which means this is a right angle right here. And if this part of it is theta, this part of it is 90 minus theta. And I work through this reasoning almost every time I do one of these things. I don't try to memorize this. Then this dashed line here is horizontal. The direction mg points is vertical, which means this angle here is a right angle as well, because the angle between horizontal and vertical is 90 degrees. And if half of that angle is 90 minus theta, the other, not half, but if part of that is 90 minus theta, well, actually it is half because theta is 45, but it wouldn't have to be. Anyway, this one ends up being theta. So I'm going to reproduce just this little triangle and figure out the part of theta that is down the plane and the part that's into the plane. And okay, so here's mg, points straight down. And this may not be to scale, but I'm not worried about that. There's a part of mg into the plane and a part of mg that's down the plane. And I want to make sure these come out kind of right angles. Okay, now this was the angle theta. This side over here is actually the, with my x pointing up the thing, it'll be the x component of mg, but it's pointing in the negative x direction. But this is the side opposite that angle theta. This is the hypotenuse. And if we had something that wasn't quite so scary looking, but I'll make a little triangle here. Okay, here's the hypotenuse. Here's the opposite side, and here's theta. Okay, the sine of theta here will equal the opposite over the hypotenuse, HYP, or that opposite side is going to equal the hypotenuse times the sine of theta. Oh, that makes this one mg sine of theta. If you do a bunch of monkeying with it, it turns out this one will be mg cosine of theta. Okay, this is the adjacent side, which adjacent over hypotenuse is the cosine of theta. Mg cosine theta divided by mg is just the cosine of theta. So convince yourself of that. This is tricky, but it shows up on an awful lot of inclined plane problems. So here's what I'll do next. I've got it, Newton's second law in vector form. Let's do it in scalar form. Let's do the sum of the forces in the y direction. Those are going to equal 0 because, again, there's nothing going on in the y direction. It doesn't fall through the plane, doesn't jump off the plane. And so this becomes, what have I got in the y direction? I've got n, and I have this thing, mg cosine theta, pointing in the negative y direction. So minus mg cosine of theta. Those equal 0. So the normal force this time is not mg, it's mg cosine of theta, which is different than what we had going on before. Now, the sum of the forces in the x direction, x points up the plane, those are going to be equal ma sub x for this mass. So they'll equal m sub l, whoops, this needs an L on it. Keep forgetting. M sub L times A sub L. And what have I got for forces in the x direction? I have the tension up there, T sub L. It's that way. And I have the component of the weight that is down the plane, mg sine theta. So minus m sub L. I keep forgetting that. M sub L g sine theta, and that will equal, oops, what else have I got? I've got the frictional force. Man, how could I forget friction? Okay, now that'll just be minus F sub k temporarily. And that'll be M sub L, A sub L. Thought something was missing. The frictional force, remember what it's like? It's equal to mu sub k times the normal force. Up until this problem, the normal force has always been mg, but we haven't done one on a tilt before. So this time it's m sub l g cosine theta is the normal force. So F sub k will equal mu sub k m sub l g cosine of theta. So this is crazy complicated already. So we'll have T sub L minus M sub L G sine theta minus mu sub K M sub L G cosine theta equals M sub L A sub L. Okay, that's a long equation and we're only halfway through. We haven't done the right mass through yet, but we should be able to do it. It's not as crazy. Here's the right mass. It's going to have its weight downward, M sub R G. It's going to have a tension acting on it, upward, that I'll call T sub R. And that's what it looks like as a vector. And for it, I'm going to let positive be downward, and it's one-dimensional. That's nice. I only have two forces, and they're both acting vertically, either down or up. And so with positive downward, I can just say Newton's second law is going to give me, whoops, M's don't have that many humps, but that's okay. M sub R G minus T sub R is going to equal M sub R A sub R. Okay, now I'm guessing you can say what some of the simplifications are going to be here. Right now I've got T sub L, I have A sub L, I have T sub R, and I have A sub R. So I'm going to do some equalities here. Magnitude-wise, T sub L will equal T sub R, and so I'll just use T's for those. And because of the directions I've chosen, A sub L will equal A sub R equals A. I don't know if they do any examples in the book that have the accelerations having opposite signs or not, but I like to do them where they're going to be the same sign, and then I can just do a substitution like this. If they're not, then one of them ends up being A and the other one is minus A, which is sort of bothersome. You have to be super careful with your algebra when that's the case. But here's what happens to my equations. This equation is going to become m sub r g minus t equals m sub r a. This one, this scary one, will become t. Hey, what if I just bring all of this stuff across? I think I'll do that. And these negative terms become positive on that side. And so the tension would just equal m sub l g sine theta plus mu sub k m sub l g cos theta. That's interesting. Plus what's already over there, m sub l a. Okay, this is equal to t, so I can substitute this in here. Oh, it's kind of painful when you do that, but let's see what happens. I'll have, I need to set up a dividing line so I don't get confused here. I'll have m sub r g minus all this stuff wrapped in parentheses. M sub l g sine theta plus mu sub k m sub l, cup's in the way, mu sub k m sub l g cos theta plus m sub l a. And that's just the minus t, and then that equals m sub r a. Wow, how many terms in this equation? 1, 2, 3, 4, 5. Oh boy. Okay, well, I'll get rid of the parentheses. I'm going to get a fresh sheet of paper, something that something I can write on here. Distribute the minus sign through. That turns every term in here negative. So m sub r g minus m sub l g sine theta. Whoops, almost wrote a plus sign. Minus mu sub k m sub l g cos theta minus m sub l a equals m sub r a. And I don't know if we got off the page or not here. Should be okay. If I kick this across, I will have m sub r g minus m sub l g sine theta minus mu sub k m sub l g cos theta is equal to m sub l a plus m sub r a. Whew. Okay, 3 terms left on the left side, 2 on the right, but I can combine these because they have a common factor. This is just a times m sub l plus m sub r. And now what? Solve for a, I guess. And this side is just repeated here. So a will end up equaling all of this stuff, a big long fraction, m sub r g minus m sub l g sine theta minus mu sub k m sub l g cos theta. That's my left side, divided by m sub l plus m sub r. Okay, and this time I can't just cancel out the m's because they're different. One thing I can do that simplifies a little bit is that there's a g in every term in the numerator, and so I can sort of pull it out here, and then my numerator reduces to m sub r minus m sub l sine theta minus mu sub k m sub l cos theta times g. And then the bottom is still m sub l plus m sub r. Okay, should I plug that into my calculator? I'd need to remind myself. Theta is 45 degrees. M sub r is 12.5. M sub l is 6.0. And you have to be super careful punching this into a calculator. So I'll just show you what I would do to be super careful. Turn on my calculator first, clear it. I want to wrap that numerator in parentheses. So left parenthesis, m sub r, that's 12.5, minus m sub l, which is 6. Now, my calculator doesn't care if I hit 6 or 6.0, so I'm just going to hit 6. And then times, I probably don't have to hit the times, but I will anyway. The sine of 45, and I teach physics all the time, so I don't have this calculator in radians mode, it's in degrees mode. And then I still have to subtract minus mu sub k. What in the world was that? That was 0.10. So I'll just go 0.10 times, and again, my calculator wouldn't have cared if I did 0.10 or 0.1, but times m sub l, which is 6, times cosine of 45. Turns out the sine and the cosine are equal at 45 degrees. And then I have to end that numerator. This parenthesis here is just ending what I put in the cosine, so have to be careful there. And I need to multiply that by g, so times 9.81. And I have to divide by a sum, and I need to wrap it in parentheses or I'd get fouled up. And it's just going to be the sum of m sub l, which is 6, plus m sub r, which is 12.5. And hopefully this won't blow up. Yes, I get an acceleration of 4 point, how many significant figures did I have? I had just 2 on most of the masses, so I'll just call that 4.2 meters per second squared. And the top term in every case is just mass. The bottom term is just mass for units. So kilograms, kilograms, they divide out, and I'll just have whatever units g is measured in, which is meters per second squared. Whew. Okay, well that was a toughie, but those were a bunch of different two-body problems, and I just wanted to spend a little time on those so you'd have some idea how we approach those. Later, like probably in the next hour or so, I'm going to be emailing your test ones out to you. And the makeup assignment will be to print the test off, and I'll include that as an attachment in the email, and resolve all of the problems, or just the ones that you missed points on. If you got full credit on a problem, there's nothing to be gained. But if you didn't, then you can make up to half of the problems or half of the points that you missed. So say you had a problem that you didn't do well on, you only got 1 out of 5. If you do it perfectly with a good solution and get 5 out of 5, then I'll average that 5 and the 1 that you had, and you'll get 3 points for it. And that can bump your grade up from sometimes a pretty dismal one to one that's at least passing, or maybe even a B in some cases. Some of you are going to pull yourselves up to an A actually by doing this. So that'll be the assignment to do. So I'll turn you loose here, and oh, Solo, you went to North, right?
Yes, I did.
Who was your first grade teacher?
First grade, I think, was Mrs. Cobb, I want to say.
Oh, okay. My wife taught first grade out at North, so, but you weren't in her class. I'm trying to remember who Mrs. Cobb was. I vaguely remember the name, but I don't remember. She always refers to everybody she works with by first names, so I never kept track of them. And most of them I never met either. Oh, Shelley Cobb, I bet was it, right?
Yeah.
That sounds familiar. All right, just curious. Okay, well, I'll be mailing those out, so watch for the tests to come in the email here soon.